Okay, welcome to Note Set 26B, Section 6.4 of the textbook. We're going to be looking at symmetric matrices and what their eigenstructure looks like. So you might think that symmetric matrices are kind of rare, but actually they show up a lot in applications for a variety of reasons. It's kind of difficult to explain, but they do show up a lot, especially in things like signal processing and communication systems and things like that. So let's motivate this idea. And this does give some idea as to why symmetric matrices show up so often, or one place where they do. So let's recall the projection matrix example that we were talking about. We already talked about its eigenstructure, its eigenvalues, eigenvectors. So eigenstructure just means, what do the eigenvalues look like? What do the eigenvectors look like? That kind of thing. So suppose we want to project R3 onto some plane. So we've got this nice blue plane over here, blue rectangle, evoking the idea of a plane going on to infinity in all directions. And we already talked about eigenvalues and eigenvectors for this. We know that a projection matrix can only have either 0 or 1 as values for the eigenvalues. And the other thing that we saw was that the eigenvector for the 0 vector are orthogonal to the plane in which we are projecting. And so this is for the R3 onto a plane example. In more general case, we might be projecting, say, like a 10th order space, a 10th dimensional space down into a 5-dimensional hyperplane, in which case there would be 5 orthogonal eigenvectors sticking out of that 5-dimensional hyperplane. But in this case we just have 1, and so we're showing that here. And the reason that has an eigenvalue of 0 is if we project that down onto the plane, it goes to the point at the origin. So that corresponds to an eigenvalue of 0. Now for the other two eigenvectors, we can actually pick any two vectors that lie in the plane of projection. So here we're showing x1 and x2. So why are those eigenvectors? Well, if I apply the projection to those, the projection is the original vector. So x1 gets projected to x1, x2 gets projected to x2. In fact, any vector in the projection plane just gets projected to itself. So that's why the eigenvalue is 1, and that's why anything in that plane is an eigenvector. But what we can do, and I haven't shown it here, let me clear some of this ink off. We are free, we only need to pick 2, right? We have 2 eigenvalues. The geometric multiplicity of this eigenvalue is 2. So it's a 2-dimensional space. We need 2 eigenvectors. So we can pick any one, and that will be orthogonal to x3 since it is orthogonal to the entire plane. And then we can pick another one that lies off, in some orthogonal direction to the first one. Now all 3 of those are orthogonal. And since we can make eigenvectors any length we want, we can normalize them. So we can choose. The key here is that we had to choose to do this. There are other choices of eigenvectors that are perfectly fine. So for any projection matrix, we've just argued, we haven't proved it, but I think you could see that the same argument will hold in general. We can choose the eigenvectors to be an orthonormal basis for the space. And that's really nice. And so now we note that, well, projection matrices are symmetric. So is this something particular to just projection matrices? or could this be true for any symmetric matrix? Now, I like to put this in here like this because it's kind of giving you an insight to how engineers think, and if you're interested in getting into research, how researchers think. So researchers establish something, and engineers do the same thing. Even if you're not doing research, you go, gee, this always works this way, and it has this characteristic. I wonder if everything that has that characteristic works that way. And that's what we're asking here. So it's kind of a way to think and come up with new ideas. And since I asked that question, it probably has to be true since it's happening in a set of lecture notes. So let's take a look at the eigenstructure of symmetric matrices, and we'll find out that, yes, we can do that. So recall that since A is being assumed to be symmetric here, that means that its transpose is equal to itself. Okay? So with a symmetric matrix for A, what can we say special about this eigenvalue, eigenvector setup here? Is there anything that we can say that's special here? And here's the answer. And we'll spend the rest of the time talking about how we know that this is true and what are some of the ramifications of this. So a symmetric matrix has only real eigenvalues. So remember in the last set of notes we were talking about how some matrices actually can have purely imaginary or complex eigenvalues and eigenvectors. So if we're talking about a symmetric matrix, that can happen. Now, this is not an only if, this is if. So if it's symmetric, it has real eigenvalues. It can have real eigenvalues, but still not be symmetric. And a symmetric matrix has eigenvectors that can be chosen to be orthonormal. So we just saw that for the projection matrix, which was symmetric. We don't just automatically get it. We have to be clever enough to say, I'm going to pick this and this as my eigenvectors. So since we can choose orthonormal eigenvectors, that lends a nice property here. So our eigenvector matrix that we've been calling S now becomes an orthogonal matrix. Remember, that means it has columns that are, it's square, and columns that are orthonormal. And so that's what we've set up here. And what do we get for that? Well, that the inverse is just equal to the transpose. So normally, for just an ordinary S eigenvector matrix, we have to compute what the inverse is. But here, no computation needed. Just flip it around, and you've got your inverse that allows you to do the decomposition. So our general eigendecomposition for a diagonalizable matrix looked like this. But now we're saying if it's a symmetric matrix, we can write it like this, where Q is orthogonal. And if you take this and you apply a transpose to that, and then use the properties of transpose, you can check that this form here is indeed actually symmetric. So that's good check to do. And so what we're showing here is that every symmetric matrix can be diagonalized, whether or not it has repeated eigenvalues or not. Because remember that the projection matrices have repeated eigenvalues. But still, since they're symmetric, they can be diagonalized. So that should tell us something about the geometric multiplicity of the eigenvalues that occur for symmetric matrices. And this leads to something called the spectral theorem. And this is such an important result that it has a special name. I have to admit that I almost wrote that it has a spectral name, but I don't think puns come across well inside PowerPoint slides. So here is the spectral theorem. It's basically just stating what we just stated. So every symmetric matrix, and we're just nailing down that it's n by n, has the factorization, or another word for that is decomposition, that we can write A, we decompose it into Q times lambda times Q transpose, where the lambda, just as we've had before, is a diagonal matrix with real eigenvalues along the diagonal, and Q holds orthonormal eigenvectors. That's a huge thing. And so then we can write our eigen decomposition this way, which we just wrote down. But if we carefully think about what this is doing, if we think about multiplying the columns of this times the elements of this, and then multiplying times the columns of this, we can work out that it ends up looking like this. And this is a remarkable result. So this result is called the spectral theorem, and this decomposition is often called the spectral decomposition or the principal axis decomposition. And applying this idea is called principal component analysis, or principal axis analysis. So principal component analysis, PCA, big buzzword in many ECE applications. Things like speech recognition, facial recognition, machine learning, all sorts of signal processing and communications, some control system stuff. So lots and lots and lots of applications where these ideas are applied. So let's take a look at this decomposition, as we call it. Clearly here we're decomposing A into a product of three different matrices. But if we look at it this way, we're actually decomposing the matrix into the equivalent. Even if we compute it this way, we can think of it this way, that what we're doing is adding up a bunch of matrices, right? Because we've got a column times a row. So a column times a row gives us a matrix. And we've got a weighting factor in front of each one. Now, the interesting thing is that each one of these matrices is just x, something times its transpose. And we've talked about this before, but we'll mention it again, that those are rank 1 matrices. And so what we can do here, what we're saying is that this spectral decomposition allows us to build a higher rank matrix A. So A might be full rank, it might not be full rank, but it certainly is likely to be higher rank than 1. We can build it up out of a bunch of different rank 1 matrices. And we have different weights on each of these. And it's easy to see that each one of these terms, something of this form, is rank 1 if we just think about what we're doing here. We're taking this vector times each element in this forms each column in that matrix. So each column of that result is just a multiple of xk. So the first column is just whatever the first element of xk is times xk. Then the second column of the result is the second element of xk times xk, and so on and so on and so on. So since every column is just a multiple of the same vector, clearly it's a rank 1 matrix. And so what we're doing is we're adding up a bunch of these. Now, I don't go into the details of this, but let's suppose that A is full rank. So then it's going to have rank n. And what we can show, I don't really go into it here, is that for A to be a rank n matrix, we would need all of these terms. So in other words, all the eigenvalues would have to be non-zero. Now suppose we found out that all of these except for the last one, and I should say we often put these eigenvalues in kind of some sort of order, maybe in order of magnitude. And so let's say that all of them except for the last one are non-zero. This last one is 0, which means we don't even really have that term. So in that case, we would have n minus 1 rank 1 matrices being added together. And we would be able to show that that would actually create a rank n minus 1 matrix. So however many terms we have adding together, that's the actual rank of the matrix. So if we know that A has rank 5, regardless of, its n by n size, there's only going to be 5 non-zero eigenvalues. That's a really, really cool thing. I didn't put it into the notes here, but it's a really, really cool thing. And just a comment, one reason why we put these in order of magnitude, descending, is that weight out in front gives it some idea of, kind of the importance or the amount of contribution that particular rank 1 matrix gives. And remember, we've made all these x's to be unit a norm. So in some sense, the size of these things are all kind of normalized to some degree. And so their contribution is measured by the lambdas. And so one way that this gets used in applications a lot is that we can kind of, we might have some matrix A and we want to approximate it, but with some lower rank version of it. So we would pick the largest. So suppose we've got a 10 by 10 matrix that's full rank, but for some reason we want to approximate it by a rank 5 matrix. We could find the best approximation by just picking the 5 eigenvalues that are largest in magnitude and keeping the terms in this decomposition corresponding to those. So I'm going a little far, a little bit afar here on the discussion, but those are the things that ECE people looking at signal processing, communications and such, image processing, facial recognition, do all the time. So let's look at an example. This example is showing the real lambdas in the matrix lambda and also showing orthonormal eigenvectors in the Q matrix. So here's a symmetric matrix. We've got 1 and 4 down the diagonal and 2 on the off diagonals. So let's find the eigenvalues and eigenvectors. And if you want to pause, give it a shot, and then come back, by all means do that. All right, let's take a look at the solution here. So we've got, to find the eigenvalues, we need to take our favorite determinant here. And when we do that, we get this polynomial, set it equal to 0. We can see that we can factor out 1 lambda, so that'll give us a lambda equal to 0. And that leaves us lambda minus 5, gives us the other root 5. So we've got our eigenvalues, and we can plug those in into this matrix here, and then find the null space of each of those. And so we'll find 2 eigenvectors, and so we find out, well, it's in the null space of this. So this actually is in the null space of A, since we're plugging in 0 here. So it's actually in the null space of A. But when we plug in 5, we're going to get A times, A minus 5I. And what we need to do is multiply that by X and see that is equal to 0. So X has to be in the null space of that. But if we rewrite this, that means AX is equal to 5X. That makes sense. So the eigenvector is in the null space of this, but look, it's in the column space of A, right? Because A times X gives us 5X. So the eigenvector is in the column space of the vector. So any eigenvector that corresponds to a non-zero eigenvalue will be in the column space of A. Any eigenvector that corresponds to a zero eigenvalue will be in the null space of A. So this is in the null space of A and in the column space of A. So we know from our study of the four fundamental spaces, we know the null space is orthogonal to the row space. So the null space of A is orthogonal to the row space. But here we're trying to see that these two things are orthogonal to each other. We can check, and they are, but we'd like to see that in general that will be true. So in general, if one of these has a zero eigenvalue, it'll be in the null space, and the non-zero eigenvalue, it'll be in the column space. But it is actually in the orthogonal to the column space, and that's because for here our matrix is symmetric. So you switch it around, row and column spaces are identical. So the null space is orthogonal to the row space, which is the column space. So we have our result. So now we can write this, since we've established that these things are orthogonal. Here's our A. Here's our Q inverse matrix, which really is just Q transpose. Here's our Q matrix, and you can check that they are just transposes of each other. And when we do all this multiplication, yes, indeed, we get our diagonalized matrix with the eigenvalues on the diagonal, in this case 0 and 5. So what we're illustrating here with this example, and also our general discussion, is that all the eigenvalues for a real symmetric matrix are real, and the eigenvectors of a real symmetric matrix can always be chosen to be orthogonal. They may be chosen to not be orthogonal, but we can always pick ones that are orthogonal. And in this example, so when I say here, I mean in this example, there's no choose needed. We were actually able to show that these the only eigenvectors that come out of this are indeed orthogonal, and that's because there were no repeated eigenvalues in this example. So here's an important example looking at a general 2x2 symmetric matrix, and we can see how this works. If you work this all out, you can actually show that this is the form for the eigenvector 1, and this is the form for the eigenvector 2, where lambda 1 and lambda 2 are the two corresponding eigenvalues. And we can see why, for this symmetric case, y x1 is always perpendicular to x2. So let's take a look. Let's do their inner product. So if you use these two forms, plug that in there, you'll get this form. And then if you just do a little bit of manipulation here, not terribly difficult, you just factor a b out of everything, add things together, and group those two together, and group those two together. So really we could write this as minus a plus c inside the end parenthesis. So the question is, why am I saying that I can show that this is equal to 0? Why does lambda plus lambda 2 minus a plus c equal to 0? And I'm giving you a hint, a word, trace of a. What does that tell you? Well, pause it and give it some thought. Maybe don't look ahead on the notes. So a plus c is the trace of the matrix. Lambda 1 plus lambda 2 is the sum of the eigenvalues. The sum of the eigenvalues is equal to the trace. Therefore, these two things are equal, and we're subtracting them. Therefore, we get 0. So basically what we're saying is that this particular example shows that what we're trying to show is that we can always diagonalize symmetric matrices using an orthogonal eigenvectors. So our matrix S becomes Q, and instead of having to do the inverse, we can just do a transpose. And it's not just that we don't have to do a physical inverse, it's that orthonormal or orthogonal matrices give us great properties. And so this becomes a real workhorse to figure out how things work. So this spectral theorem, it has a special name, so it's pretty important, and we really should at least make some attempt to prove it. So there's a few parts to it that we can prove in various steps. So one part was that all the eigenvalues are real, so we can prove that by itself. So symmetric matrix, all real eigenvalues. Then we can easily prove the orthogonality for distinct eigenvalues for a symmetric matrix. Again, that's pretty easy to prove. The third part, to be able to prove the orthogonality for repeated eigenvalues, considerably more difficult, and I just punt here. The book does a kind of a rough proof of something called Schur's theorem. So I don't show that proof. I don't take you through that here. You can read it in the book. And then from Schur's theorem, boom, we get our result almost immediately. So we are going to run into having to talk about complex numbers. I mean, if we're trying to show that things are specifically real, we need to start off assuming that they're complex, potentially, and then show that they aren't really complex, that they are real. So we need to have some handle on how to manipulate and talk about complex numbers. So let's say that Z is a complex number. That means that it has A plus JB. So I'm using J as ECE people do to represent the imaginary number. So we say A is the real part, B is the imaginary part, B is the thing that gets multiplied times J. A and B are both real numbers. So a complex number has one real number plus J times another real number. And this form is what we would call rectangular form, because we can think of the A and B as residing on two different axes, the real axis and the imaginary axis. Okay, that's about as far as we really need to go thinking about that. As you move further into your ECE classes, you'll need to know much more about complex numbers. So the only other concept we need right now is this idea of a complex conjugate of a complex number. So all that is you give me Z, and then I say, so there's this other number, which is the complex conjugate, which I will indicate as Z bar. And all I do is I have to negate the imaginary part. So if I wrote it as plus JB, I now write it as minus JB. Now, it doesn't matter whether B itself is positive or negative. That's not important. The act of putting plus here and negative here will negate the imaginary part. So that's all we really need to know and feel comfortable about. So here's our statement. All eigenvalues of a real symmetric matrix are real. So here's our proof. We're going to assume that the eigenvalues and eigenvectors could be complex. So in particular, that means that each lambda could have this form, A plus JB, for some A and some B. And if they truly are complex, the B cannot be 0. So let's start with this. This is our fundamental equation that defines eigenvalues and eigenvectors, and we'll call that equation 1. Now what we're going to do is conjugate this. So notice that I pronounced the word slightly different. If I'm talking about it as a noun, this is the conjugate, I say it that way. If I want to talk about the act of making the conjugate, I call it conjugate. So I'm going to conjugate and use the fact that A is real. So the conjugate of A is just itself, since it has no imaginary parts. Changing their sign on a bunch of zeros doesn't do anything. So if I take this thing and I take the conjugate of the left side and I take the conjugate of the right side, well, another property is that the conjugate of the product is the conjugate of individuals. So that would give me A conjugate X conjugate, but A conjugate is equal to A, so I leave A. But over here I've got lambda X, whole thing conjugate, breaks down into lambda conjugate times X conjugate. Now I'm going to take the inner product of X conjugate with equation number 1. So here's equation number 1. So I'm going to take X conjugate and bring it in from the left with a transpose. So conjugate transpose times AX, that's right there. And then lambda's a scalar here, so I can pull it out in front. Lambda, and then here's my X conjugate transpose coming in from the left, hitting X up here. So now I've got a new equation. Now I'm going to do the inner product of 2 with X. Now notice the ordering that I said. Of X conjugate with 1, of 2 with X. So this just means that the whole equation 2 is coming from the left. So that means I need to transpose this, which will switch the order, and that gives me conjugate transpose times transpose of A, but A is symmetric, so no transpose on A. And then I'm coming in from the right with X. So there it is. And then on the left side, I've got lambda conjugate, which I pull out in front. That's a scalar. I transpose that, and then the X coming in from the right. So I've got that. So now we look at that and we say, well, the left sides are equal. Let me clear some ink here. The left sides are exactly the same. That's what we were aiming for, to set up two things that are equal to each other. But look at this. This is the same, but these things are different. But yet they have to be equal. So I'm going to set the right sides equal to each other. So I have that. Now, what is this? X conjugate transpose times X. Now remember, we said that the X's could be complex. So let's look at what that does. If we work that out and use a little bit of complex number theory, that conjugate times itself is the magnitude of that complex number, we can get this result. And so these are the individual elements of X, magnitude squared, and we add them all up. So that certainly has to be greater than 0. So that means I can divide this thing away, right? So it's on both sides, so I can get rid of that on each side. And so what does that do? So that then says that lambda must be equal to lambda conjugate. And since I said lambda was being assumed to have a complex structure, a plus jb, it says a plus jb is equal to the conjugate of that, which is a minus jb. So the real parts are equal to each other. The imaginary parts have to be equal to each other, but with a negative sign. So that means that negative b must be equal to b, and the only way that can happen is if b is equal to 0. And when b is equal to 0, coming back up to the top, that means lambda is actually purely real. And so lambda is real. So we just proved that the eigenvalues must be all real. We didn't say anything about the eigenvectors, but we could do a similar kind of thing to show that if the eigenvalue is, well, it's actually easy to see that, right? If the eigenvalue is real, we should be able to easily establish that the eigenvectors are also must also be real valued. So we didn't prove that, but it's actually pretty easy to see. Now let's take a look at the orthogonality. But as I said, in step 2, we're going to do this only for distinct eigenvalues. So here's our proof. Let's pick two eigenvalues that are not equal to each other. That's the distinct part. And we know that this equation then holds, and this equation then holds, where x1 is the eigenvector corresponding to lambda 1, and x2 is the eigenvector corresponding to lambda 2, and lambda 1 and lambda 2 are not equal to each other. So let's take this first equation here, take this thing, do an inner product of the first equation with x2. So I'm reversing the order of this, so I'm dealing with the right side up here becomes the left side down here. So I get this structure where I've used the fact that A is symmetric. So I do not need to keep the transpose on A. Now I'm going to do an inner product of x1 with the second equation. So I'm because of the way I've phrased this, I'm bringing x1 from the left. So I get a transpose on x1 because I'm bringing it into an inner product from the left. And now the right sides are equal, so the left sides must be equal. But notice that these two things are the same, and so those two things are equal to each other. And but we know that lambda 1 cannot be equal to lambda 2. We assumed that up at the top. So since they are not equal to each other, and we have something times lambda 1 and that same thing times lambda 2, but lambda 1 and lambda 2 are different, the only way that can work is if x1 inner product with x2 is equal to 0. Or in other words, x1 is orthogonal to x2. So look at that. Wasn't that such a nice little slick proof? So now let's deal with the repeated eigenvalue case. And as I said, as we were laying this out, we're going to address this using Schur's theorem. So this is a nice general theorem. We're not going to prove it. The book has a rough sketch of the proof. But Schur's theorem says that every square matrix, there's no symmetric here. This is every square matrix can be factored this way, where Q is clearly orthogonal and T is some upper triangular matrix. So this looks like a pretty useful and snazzy little decomposition. And it goes on further. It says that if A has real eigenvalues, then Q and T can be chosen to be real as well. So that's good. And we get that Q transpose is actually equal to the inverse, which we stated up at the top as well. Now, so given that that's true, and again, I'm not proving that here, but the book does go through it, how does this establish our diagonalization for the symmetric case? Well, it certainly gives us the real eigenvalue part automatically, since we know when we have a symmetric A, we then do have real eigenvalues, so we get this result, and we know that Q and T can both be chosen to be real. Just had a little interruption there that I'm going to edit out, and I can't remember where I was, what sentence I was in the middle of. So if we have a symmetric A, we get the real eigenvalues, and we get that Q and T can be chosen real. So up here it said nothing about Q and T being real valued, so we get that automatically for the symmetric A, and we get that Q transpose Q is equal to the identity matrix. But we still don't know anything about diagonalizing, right? T is an upper triangular matrix. But let's see what we can do. So since we know this is true, we can now write T, moving all of these things over to the other side, we can write T is equal to Q transpose A times Q. And again, that's easy to verify that that is symmetric. So what we've just shown is that applying Schur's theorem to a symmetric matrix A, the T must also be symmetric. But we know it's upper triangular as well. So think about it. Something that is both upper triangular and symmetric, only way that can happen is it has to be diagonal. So we didn't prove Schur's theorem, but we proved that Schur's theorem implies that every real symmetric matrix is diagonalizable, even if it has repeated eigenvalues. So let's summarize all this stuff. Any matrix with no repeated eigenvalues can be diagonalized. Doesn't matter if it's symmetric or not. If there are no repeated eigenvalues, we're good to go. If there are repeated eigenvalues, might not be diagonalizable, but if it is symmetric, then it can be. It doesn't have to be symmetric to be diagonalizable. So there are some that are not symmetric, have repeated eigenvalues, could be diagonalizable. But if it is symmetric, we know that it will be diagonalizable. So all symmetric matrices are diagonalizable. Now let's talk about the fact that we can have some complex eigenvalues. Real symmetric matrices prohibit that. We end up with all real values. But matrices that are not symmetric, it's possible for them to have all of its eigenvalues real, but it's also possible that some or all of the eigenvalues of a non-symmetric matrix could be complex or even purely imaginary. So for a real matrix, if there is a complex eigenvalue and eigenvector, then their conjugates are also an eigenvalue and eigenvector. So they must appear in complex conjugate pairs. So in other words, you give me an x and a lambda. If they're complex and I plug them in here and they work, then I can also plug in x conjugate and it will give me lambda conjugate times x conjugate. So if you tell me eigenvalue is 5 plus j2, I know that 5 minus j2 is also an eigenvalue. And the corresponding eigenvectors will be complex conjugates as well. And so let's finish this off. I think this is the last slide. I love to make these little kind of Venn diagrams so that it helps me keep track of what's what. So here's all real matrices. Doesn't matter. Well, I really should say square. So let's make this square. So I should modify this, and I'll try to change this. So all real square matrices, since we're talking about eigenvalues. So there they all are. Let's add in all those that have real eigenvalues. So this whole ellipse here is matrices with all real eigenvalues. Now, if we look at this outer ring here, just apart from here out, some / all eigenvalues of those out there are complex and appear as conjugate pairs. Okay? Now we add in another ellipse. Let me clear off some of the ink here. So this ellipse is symmetric, real symmetric square matrices. And so inside there, we know that the eigenvalues are real and the eigenvectors form an orthonormal set. So in the ring outside there, but not any further out than here, we've got eigenvalues are definitely real, but the eigenvectors might not be independent. Now remember, there are some that aren't symmetric that are independent eigenvectors, but there's certainly going to be some out there that have dependent eigenvectors. So hopefully that kind of helps you visualize the results that we've been seeing, and we'll pick this up in the next set of notes where we'll extend this to the idea of something called positive definite matrices, which, yeah, you guessed it, play a big role in electrical and computer engineering. We'll see you next time.